All right, so we are about to define a power series, but I wanted to show you guys this one before we do that. This is really just building off that last intro example we did where we approximated uh, e to the x centered at 0. And so I've actually got that just back up here. E to the x centered at 0 would give this power series. Okay, so what if we wanted to approximate e to the x but centered at 2? How would that work? And I notice here I've got a mistake here in my p sub n, so I'll go ahead and fix that while we talk. If you did this and you followed all those same guidelines and you came to your nth degree polynomial, it would follow this power series. So e to the x from 0 to infinity summation e squared over n factorial x minus 2 raised to the n. So we can start to see some changes, but also some similarities to that last one. So first thing, what you really notice is that 1 becomes e squared, right? So if we're centering at 2, then we're concerned about f of 2, which is e squared. So it comes out there. Also, the x, this was centered at 0. When we center at 2, we have to then subtract 2. It's almost like to shift it back to get it centered at 2. So if we plug 2 in for x, let's say, then that's where we're centering, right? Okay. So if we were to write out the nth degree polynomial, and I notice I need to make some changes. So the 0 term would be e squared, not 1, right? Then the next term would be e squared x minus 2, and it's going to follow that same style, but now with e squareds throughout, if we did n terms. Okay, so how is that helpful? So that's going to help us wrap our head around the power series definition. So we say a power series centered at C. Okay. And it's not unusual for us to center at 0, but we might center elsewhere. Okay. It's going to look like this. N equals 0 to the infinity. Some nth term, a sub n, followed by x minus c raised to the n. And so the difficult part is just that a n, right? So we know it's always x minus where we're centering to the n power. But this could change drastically from problem to problem, as we saw in the last one. But let's just kind of explore this in general for now. Given that we know where we're centered, for what values of x will our power series converge? Okay, so that's what we're interested in. And we saw it back in the graph in that intro example. If we got very far away from 0, right, then the two curves started to diverge. But when we were near to 0, then the two graphs were very close together. And that's what's always going to happen. So the further away you get from where you're centered, they start to spread out more. So we'd say when you're close and it's a good approximation, you're converging. But the further out you get, you are diverging. So let's investigate. Hey, what if we just take x to be c itself? What would happen at c itself? Think, okay, here's what we're going to do. We're going to take c, and we're just going to plug it in there for x in our power series. Say, okay, so if x equals c, let's just see what happens. So, well, that's going to be 0, 0 to the n. Think about that series right there. If you listed out a bunch of terms, the 0 term would be a0 times 0 to the 0, right? Well, 0 to the 0 is 1, so that would be a0. But as soon as you get to n equals 1, then we're now multiplying by 0 to the first, 0 squared, 0 to the third. Every other term that we're adding after the 0 term is 0, if that's not too confusing for you. So this whole thing would simply add up to a sub 0. Well, that converges, because we get a finite sum. So at C itself, our power series is always going to converge. The question is, what happens as we get further away from C in both directions? So here's a theorem, and I've got a little note as part of my theorem. Let me just show you the whole thing. Okay, so it says, for the power series, n equals 0 to infinity, a sub n, x minus c to the n. By the way, we call it a power series. That sounds, it's kind of a cool name. Power series sounds strong, you know, I think. But where does it come from? Because we've got a power, right? A power of n, power series. Okay, so for your power series, there exists capital R greater than or equal to 0. The capital R is the radius of convergence. So we're thinking as we move away from C, we'll move an equal distance both directions. That's our radius of convergence. There's a radius of convergence that's greater than or equal to 0, such that if the distance from x to c, otherwise known as the absolute value of x minus c, how far away are you from c in either direction, if that is less than your radius, then you are converging absolutely. Okay, so if you're inside your radius, you converge. But if the distance from x to c goes beyond r, if you move further away than your radius of convergence, then you diverge. And I've got a simple picture here for you. So imagine, you know, got a number line here. C is right there at the center. So we know it at least converges at C. But if we have some kind of a positive radius and we can move outwards in either direction, that distance, then everything in here, all the x values inside that radius converge absolutely. And it's absolute because, you know, we're moving the same distance in both directions. It might happen that, well, I don't want to confuse. I'm going to stop there. This is what we need to know. If we go beyond our radius of convergence, then we diverge. We diverge if we get too high, we diverge if we get too low. Okay. All right, I think we're going to stop. Oh, you know what? One other thing I got to mention before we stop this video. Comes right off radius of convergence. There's also the interval of convergence. I almost forgot about this. The values of x for which the power series converges. So there's a radius. That's the radius is the distance, right? How far can you go? The interval is what the actual values are. So if you thought, okay, if I move this direction r, then that's c plus capital R, and this is c minus capital R. So we're going to find what these numbers are. We're going to find the radius. We're going to find where these occur based on where we're centering, and that's going to lead us to the interval of convergence. Now, one thing, we have not mentioned what happens at the endpoints. We know that we converge in the middle, but on the endpoints, sometimes you converge, sometimes you don't at those endpoints themselves. So we're going to figure out a way to test the actual endpoints on our interval. We're going to do an example in the next video.